So these are the two samples that we will be using today. So firstly, we're going to start off with the XRF sample preparation. So in my hands, I have the containers that we're going to use as well as Mylar tin film. So placing the Mylar tin film to prepare the container for the XRF sample, I'm going to place the sample container, press it onto the Mylar film, and to ensure that the container is well prepared, there should be no bubbles or no scratches below the container. That there is the cap for the container, and using our first sample, sample 2, I am going to put some of this unknown composition into the container. As you can see, there are no bubbles below. So starting off, first I'm going to do the calibrations for the XRF. So I'm going to do the energy calibration, and this is using a copper sample. I'm also going to do an energy calibration check, a vacuum calibration, both of which are also done using the copper sample. So this here is me simply placing the copper into its respective location on the software, and it is assigned a location within the XRF itself. The other calibration that will be done is a quality check calibration, and this is done using a glass sample. And this also has a specified location on the tool itself. So now that these are in their respective spots, I'm going to start it, and the XRF is run using helium. So in here, we have sample holders A, B, and C. And here we would have placed sample 2, 4, and 6. However, as you will see later on, sample 4 was omitted because of its similarity to sample 2. And here we're simply adding the different samples and placing them into their respective locations as we previously did. So we're putting the samples into the software, and the film that we were using was Mylar film, which has a thickness of 3.6 micrometers, and we are inputting this information into the software. So again, this is me placing the samples into their locations on the software. Now, following that, collecting that data, now we're going to do the XRD sample preparation. So this technique that is being used to prepare the samples is called backloading. So essentially it consists of a sample holder, a funnel, and this is me placing the sample into the sample holder and ensuring that it is spread enough. I ensure that the moving around the sample, it was done lightly to avoid damaging the particle surface. And this is me gently pressing the sample into place, again, not damaging the surface of the particle. This here is the cap. I'm placing it with the prongs up. And here we have our prepared sample for XRD. Now, I'm ensuring that the level of the sample is leveled with the sample holder to avoid this sample displacement error. And this is me placing it into the XRD. Now, the air scatter screen used was 3 millimeters, and the divergent slit, this is me showing 3 millimeters, and the divergent slit used is 2 millimeters. So this is me closing the XRD, and First, we get our sample spinning. So the specification that was used was 10 rotations per minute. And if you look very closely, you can see that the value for phi is changing, which means that the sample is rotating. And now that the x-rays are turned on, I can go ahead and input my values, my specified values, which the sample will be run. So the values that were input were used consistently for samples 2 and 6 since 4 was omitted. And here we used a range of 20 to a two data range of 20 to 80 with an increment of 0.02, a time per step of 0.01, and the PSD opening was set to a maximum. This here is the data being collected. What you're seeing here is background. Following the sample prep and data collection on the calcium fluoride and zinc oxide, we will now be looking at the XRF and XRD analysis. Looking at the XRF results for sample 2, we found that there was 27.6% of calcium and 70.3% of zinc. We will be assuming that all calcium detected is in the form of calcium fluoride and all zinc detected is in the form of zinc oxide. This is assumed because fluorine and oxygen are lightweight elements and could not be detected by XRF. So assuming that there is 100 grams of sample 2, we can calculate that there is 28.2% of calcium fluoride and 71.8% of zinc oxide. Moving on to sample 6, we found that there was 56.83% of calcium and 40.2% of zinc. With the same assumptions and assuming that there is 100 grams of sample 6, we can calculate that there is 58.5% of calcium fluoride and 41.5% of zinc oxide. This is the XRD spectra for sample 2, and these are the peak locations as well. Using the peak locations or the two data values, we can use a series of calculations to calculate the H, K, and L planes. So using Miller indices, we were able to calculate the planes for calcium fluoride being that it is cubic. For the zinc oxide, however, that has a hexagonal structure and its formula for calculating the planes were a bit different. So for calcium fluoride, we could have used the formula H squared plus K squared plus L squared to get the HKL planes, whereas for zinc oxide, the formula is H squared plus HK plus K squared. And for that reasoning, we would have used the ICDD cards to obtain the HKL planes. So here shows the peak locations as well as the HKL planes for calcium fluoride and for zinc oxide respective to sample 2. This is the XRD spectra for sample 6. This here is a peak list for sample 6 from the XRD results. So using the two data values, again using the same series of calculations for sample 6, we can calculate the HKL planes for calcium fluoride, and using the ICDD cards, we can obtain the planes for zinc oxide. Now if you can see the HKL calculations using the two data values all match for calcium fluoride. Again, these are the respective peak lists for sample 6 as well as the HKL values. And this graph here shows sample 6 and sample 2. It does include sample 4, however, sample 4 was removed because of its similarity to sample 2. From the results, we can see that calcium fluoride is face-centered cubic and zinc oxide is hexagonal. And using the Miller indices, we were able to look at their HKL values to determine this.